Thank you. Thanks to the organizer for inviting me. I am sad I could not be in Tokyo, and this makes the interaction with you not so easy. But please interrupt me, ask questions during the talk. I am particularly glad to celebrate Toshiyuki Kobayashi 60th birthday with you. I have been knowing him for more than 30 years. And I have very small anecdote. In fact, he is the first person to whom I asked a mathematical question through internet 30 years ago. And it was a really impressive experience at that time to ask a question to a mathematician on the other side of the earth. And within a few hours, to get the answer to your questions. So it was very nice. And today, for this opportunity, I have chosen to discuss a very elementary topic. And this kind of topic that makes you, I guess, at least was for me, that makes you love mathematics. Okay, so the title is Convolution and Square in abelian groups. And the talk will be divided in six sections, 6 parts. So let me see these 6 parts here. So first, I will introduce this elementary topic, which I call critical values. I give this name. You can choose another name if you want. And once I will have given the definition and the elementary properties of critical values, in the second part, I will give example of critical values. And that's the magic part of the talk. That's where you see a list of critical values. And really, you want to know where do they come from. I will get these critical values from numerical experiments. And we will see them. And we will really want what kind of mathematics is hidden behind these critical values. And the answer will be in the following parts. So what will be hidden will be abelian varieties, and more precisely, abelian variety with a complex multiplication. So complex multiplication CM number fields. And also what will be hidden will be theta functions. And those theta functions, the important point of the important property of the theta function in this talk will be that they are modular forms on the Siegel upper half space. And so we are back in what we love in this conference, a nice Riemannian symmetric space, Hermitian one, the Siegel upper half space. And I will end this talk with 2 open questions. Okay, so that's the program. So I begin now by introducing this very elementary topic that I was telling you. Those are the critical values. So this slide is very important because here is my definition, and I will use this definition all over the talk. So, and since I don't have a blackboard, I cannot leave it on the screen during the whole talk. So please remember it. And so the data is very simple. What you have is just a finite abelian group. And you assume that the order of this group is an odd integer, just to simplify. And what I want to understand are functions on this group So this function live in a finite dimensional vector space, complex valued function, which satisfies a nice functional equation. The convolution square here, this is the convolution square. You see the sum x plus y plus x minus y is 2x. So it's a convolution square computed at the point 2x. So it's a small switch, which is in fact important, but and I want the convolution square to be proportional to the usual square. And this proportionality constant, lambda, for a non-zero function f, will be called a critical value on G. And the associated function will be called a lambda critical function on G. A very important example is when G is a cyclic group, Z over dZ. And in this case, I will just say that a lambda is a D critical value. Okay, so that's my definition. And I will spend the whole talk trying to understand critical values. And at the end of the talk, I will understand just part of it. Okay, so let me begin, before giving examples, let me begin with easy properties of critical values. So 4 easy properties that are here and that I will use during the talk. So assume lambda is a critical value of G. The first property is that in absolute value, lambda is bounded by D. And the reason is that if you look at the inequality, the equality, the defining equation, you just apply Cauchy-Schwarz inequality to this defining equation. And you get that lambda has to be bounded by D. I leave it to you as an exercise. The second property is that when lambda is a critical value on G, then D over lambda is also a critical value on G. And again, it's very easy to prove this fact. The reason is you just apply Fourier transform to your equation E. You apply Fourier transform, and by Fourier transform, square becomes convolution, convolution becomes square, and there is some, so the lambda becomes 1 over lambda, and there is a D because of the usual property of Fourier transform. So you get that D over lambda is also a critical value. The third property, which is a nice property, is that when lambda is a critical value, I can consider all the Galois conjugate of this complex number, all the image of lambda by automorphism of the complex number. And then I also get a critical value. So all the Galois conjugate, just because the equation E has integer coefficients. Okay, it's again an easy property. And the last property is a nice one, is the fact that lambda is an algebraic number, but even better than an algebraic number, it's an algebraic integer. And it's even better, not only lambda is an algebraic integer, but lambda minus 1 over 2 is an algebraic integer. And maybe I give a little hint how you get this information. Where does the lambda minus 1 over 2 comes from? You just look at the equation E here, and you see that on the left-hand side, you already have some f of x squared when y is equal to 0. So this f of x squared, you can put it on the right-hand side. So you get lambda minus 1. But then the other term, when y is not 0, they appear twice because they are the same for y and minus y. So this is why the equation E can be rewritten as an equation of the form lambda minus 1 over 2 f of x squared equal a sum of f of x plus y, f of x minus y, but it's a sum only on half of the y, not all the y. And from this equality, you get that lambda minus 1 over 2 is an algebraic integer by proving that when you apply to this equality, when you apply to this equality non-Archimedean absolute value, then you get that lambda minus 1. It's a little trick. You just check that the non-Archimedean absolute value of lambda minus 1 over 2 are always bounded by 1. And this gives you that it is an algebraic integer. So I don't want to say more. Just wanted to explain to you that it's not difficult fact. So we have these 4 easy properties of critical values, which are nice because you see, we will know that a lambda is an algebraic integer, but d over lambda is an algebraic integer. So it's not so easy for both lambda and d over lambda to be integers. So this tells you that there are lots of constraints on these critical values. So here is my definition, and here are my first properties. And now I am switching to examples. If there are no questions, I'm going to examples. So maybe before going to examples, I will just say that because of this proposition, for given group, you have only finitely many critical values. But what will be surprising, and which will be a consequence of this talk, is that when you fix G and lambda, very often we will have infinitely many lambda critical functions. So the space, the algebraic variety of lambda critical functions will be higher dimensional, which is for me a surprise. And also a remark, what would happen if you take, instead of a finite abelian group, you take the real, and you consider the same convolution equation, f convolution with f in 2x is proportional to f of x squared. Then you have a nice solution, which is f of x is a Gaussian function, e minus alpha x squared minus beta x minus gamma for a real part of alpha positive. So it's a Gaussian function. Gaussian functions give you examples of critical function on the real. I don't know whether there are others. That's a question I don't know, but I don't want to discuss this question today. What I want to discuss is the question on finite abelian groups. So let's begin with this example. I want to choose a finite abelian group which is not too small, maybe not z over 3z, so slightly larger. I will take a abelian group of order 11. So if there is only one, it's a cyclic group of order 11. I have recalled here the definition of critical value. And here is a list of what I expect to be all the critical value over the cyclic group of order 11. And this is what I told you at the beginning of my talk. This list is amazing. When you see this list, you really think there is something at hand, and I want to know what is hidden behind this list. And this is what I want to try to explain to you in this talk. So you see, it looks like a long list, but in fact, it is not. It's a very short list because part of this list is completely trivial. So let me first begin by explaining to you the trivial part of the list. First, there is this critical value lambda is equal to 1. So this means that I have to be able to find a function which satisfies this equality with lambda equal 1. If I were with you in the room, I would ask someone in the room, but it's not so easy to do it by internet. So I will give you the answers right away. So for lambda equal 1, the corresponding function f is just the Dirac mass at 0. So it's a function whose value is 1 at 0 and which is 0 elsewhere. So lambda equal 1 is really a trivial thing. Lambda equal 11 is also completely trivial because you just take the Fourier transform of this one. So you just take f to be the constant function. So if you replace f by 1, since G has 11 elements, you get that 11 equal 11. Okay, so now there is this one, the third one. This one looks more interesting, but in fact, it's still a trivial one. The reason is just look for f, which is constant outside 0. So f will just take two values, one value at 0 and one value outside 0, like the first one. And so this gives you a equation in lambda, and in these two values, you solve them easily. And you get that there are more solutions than 1 and 11. There is also 4 plus square root of 5 and 4 minus square root of 5. So this list I'm giving to you is just up to Galois conjugation. Okay, so here these three values are easy. And then there is this one. Lambda is equal to I square root of 11. Again, if I were in the room with you, I would ask you, what is the corresponding functions? Because you can't find the answer to this question. The corresponding function, it's again an easy critical value. The corresponding function is a Gaussian function. F of x is a Gaussian. It is zeta to the minus x squared. Exactly like over the real numbers. Same kind of formula with, but since x here is an integer modulo 11, I have to choose zeta to be an 11th root of unity. Okay, and why does it satisfy this equation? So just do the computation very quickly by yourself. And you see what you have to use is just the following formula, which is that the sum over y of zeta to the power minus 2y squared, which is a Gauss sum. And we know how to compute this Gauss sum. It's a Gauss sum over the field with 11 elements. So it is equal, according to Gauss, to I square root of 11. Okay, so we find that the first four critical values are trivial ones. And now that's the intriguing part of the talk. There is these two eigenvalues, 2 plus I square root of 7 and 2 square root of 2 plus I square root of 3. And there is this one. To understand these eigenvalues, for this one, we will need elliptic curves. And for this one, we will need abelian variety of dimension 2. And we will need another thing here. We will need to notice, what is very important is to notice that this number, 1 plus square root of 5 plus I square root of 5 minus 2 square root of 5, is in fact a nice product. And let me write to you why it is a product. Let me try the product. It's a kind of classical formula from the 16th century. Let me write it. It's equal to 1 plus I is square root of minus 1, as you guessed. I square root of 5 plus square root of 5 over 2 times the same thing with some minus. So a Galois conjugate of this element. 1 minus I square root of 5 minus square root of 5 over 2. Okay, this product formula will be very important in the rest of the talk, because what I plan to do now is to see that this special case of critical values are part of critical values that I can construct with abelian varieties. But before doing that, I will put them in nice families. So the first family here is part of the following proposition, which is this proposition here. Each time you have an odd integer d that you can write as a sum of two positive integers. For instance, you can take 11 and you write 11 as 4 plus 7, or you write 11 as 8 plus 3. So there is a condition on a condition mod 4 here. That a has to be equal to d plus 1 square over 4. D plus 1 is an even number because d is odd. And so d plus 1 square over 4 is an integer. So you have this condition mod 4 on a. When it is satisfied, like here, square root of a plus I square root of b will be d critical. But I don't know any elementary proof of this fact. The proof, as you will see, will rely on elliptic curves with complex multiplication and Jacobi theta functions on these elliptic curves and the modular property of these Jacobi theta functions. You may wonder Why am I doing this strange congruence condition on A? So in fact, this condition is very natural because when you define lambda as the square root of A plus I square root of B, this condition is just the fact that lambda minus 1 over 2 is an algebraic integer, as we have seen. So it is in fact a necessary condition. And what this proposition is telling you is that this necessary condition is in fact sufficient for this lambda to be D-critical. Okay, so this was the nice setting for this family of eigenvalue. And for this eigenvalue, there is also a general family which contains this one. And this is the following proposition. This time you don't write D as a sum of two integers. You write D as a sum of three integers. So like, for instance, you write 11 is 1. So let me, can I keep it? Yeah, I want to keep it with my, it's too far away. So this number is a special case of what I'm writing now. So A is equal to 1, B is equal to 5, and C is equal to 5. So I'm writing D as a sum of three positive integers, for which the discriminant B squared minus 4AC is strictly positive. And then in this case, we will see that under some congruence condition, A, B, C equal to 1 mod 4, condition which ensure that lambda minus 1 over 2 is an algebraic integer, then this algebraic number, this algebraic integer, square root of A plus square root of C plus I square root of B minus 2 square root of AC, is always critical on the cyclic group Z over dZ. And when this congruence condition is not satisfied, because A, B, C, for instance, are equal to 3 mod 4, then lambda minus 1 over 2, in this case, is not an algebraic integer. But if you multiply lambda by fourth root of unity, like I have done here, and then doing some complex conjugation, when you do that, it becomes, the lambda minus 1 over 2 becomes algebraic integer. And then this is why, for this case, we have a slightly different formula for the associated critical value. Okay. And now what I notice is that in all these examples, it's a nice remark, in all the examples, my critical values, lambda, have absolute value equal square root of. In proposition 2, in proposition 3, all of them satisfy this condition. But again, here, I will not be able to find elementary proof, and this will rely on abelian surfaces with complex multiplication. Are there questions?
Not yet.
Not yet. Okay. Please ask. I'm kind of concerned. I'm speaking.
There's one question. Just a second.
Sorry.
There's one question.
Is it your list is exhaustive or not? I mean, is there any other?
No. It's just a list of critical value, and that's really an important question that remains at the end of the talk. I don't know the whole list. Even for D equal 11, I don't know the whole list. I gave a list. I think it is a full list, but I have not a complete proof that it is a full list.
Thank you.
But as you see, we will have a very nice and very surprising construction of critical values that I now explain. So here is, to explain this construction, I have to recall you what is an abelian variety. So let A be a principally polarized abelian variety, PPAV. This means that A is a abelian variety. First, it's a complex torus. So it's a quotient of the Cn by a lattice. This lattice is a group isomorphic to Z to N. But not all complex torus are algebraic varieties. So those for which the quotient is an algebraic variety are called abelian varieties. And a nice condition, well-known condition, is that it has to be polarized. And it's if and only if you need to find a positive Hermitian form on Cn, H, whose imaginary part, which is a symplectic form, takes integral values on the lattice. So this is what is called a polarized abelian variety. And principally polarized, you have the condition that the symplectic form has covolume 1. So you can always replace lambda by a commensurable group in Cn, for which your abelian variety, polarized abelian variety, becomes principally polarized, if you want. So this is the definition, the very classical definition of principally polarized abelian variety. And when you have a principally polarized abelian variety, there is a very natural Q algebra associated to it. It is the endomorphism of your complex space that preserve the Q vector space spanned by lambda. So it's a Q vector space inside Cn. And so this Q vector space is invariant by nu. So you can introduce the restriction of nu to this Q vector space. And you call this the holonomy of nu. Nu does not preserve lambda. It preserves only the Q vector space spanned by lambda. So this is the algebra of Q endomorphism of the abelian variety. And there is a nice remark, is that this endomorphism of Cn, because of the relationship between the symplectic form and the Hermitian form, the Q endomorphism nu is unitary for H, if and only if its holonomy is symplectic for omega. And now is the main and the only theorem of this talk. So if there is something you have to focus on, so this theorem is just a very short one. So the data is a principally polarized abelian variety, and with it, a unitary Q endomorphism. And I assume that this Q endomorphism nu satisfies some congruence condition that I can express easily. So I write H nu, it's a symplectic matrix. Of size 2n with rational coefficient. And the congruence condition is that this matrix has to be equal to 1 mod 2. And if you write it as block matrices, block matrix alpha, beta, gamma, delta, beta and gamma have some diagonal. So the diagonal coefficients are called beta ii. And I want them not only to be even, but to be divisible by 4. They have to be equal to 0 mod 4. So this is a very small congruence condition that I will explain again later. So, okay, and this was the assumptions. So the data is a principally polarized abelian variety with a unitary endomorphism. And the conclusion is I can construct with that a critical value, lambda, which will have the property. So this critical value will be on the following finite abelian groups. It will be the quotient of my lattice lambda by its intersection with new lambda. So new lambda and lambda are commensurable. So this quotient is a finite abelian group. And so I called d nu its order, the order of this group. And the lambda I will construct will be a critical value whose absolute value is the square root of d nu, as before. And so this lambda has a modulus, which is the square root of d nu, and it also has an argument. And this argument is just the square root of the determinant of this complex matrix. Nu is a complex matrix. So it has a determinant, and I take the square root, is defined up to sign, but here I'm not so sure lambda is a critical value. What I can say is either lambda or the multiplication of lambda by some fourth root of unity is critical on G nu. So I just know my critical value up to a fourth root of unity. Okay, and so this is the main theorem of the talk. So what I want to do now is two things. The first thing is to explain why proposition 2 and 3 are special case of this theorem. It's not clear, a priori, why they are a special case of this theorem. So I will do it right now. So what do you do for, how do you prove proposition 2 from this theorem? So what you want to prove is that square root of a plus I square root of b is d critical, starting from this formula for lambda. So what you do is you use elliptic curve. So the dimension n is 1. And this will be the lattice. And what you choose for unitary element is a multiplication on C by this complex number of modulus 1. Square root of a plus I square root of b over square root of a minus I square root of b. It does not exactly preserve lambda. It sends lambda to some commensurable lattice. And you can check that the group is z over dz. And now, what does this formula for lambda gives me? It gives me that lambda is equal. There is this fourth root of unity, I forget about it. There is a square root, and there is this d. D is a plus b. And then there is this determinant. But you are just in dimension 1, so it's just nu. So it's square root of d nu. And d is a plus b. So you write a plus b as a square root of a plus I square root of b times square root of a minus I square root of b. So you have a simplification, and you just get that lambda is a square root of a plus I square root of b. And that's the way I get proposition 2 from theorem. So the same is true for proposition 3. Let me explain it very quickly. And let me show you that what is important in the argument is the factorization formula I gave to you at the beginning of the talk. So I want to prove that the square root of A plus square root of C plus I square root of B minus 2 square root of AC is D critical. So for that, I use an abelian surface, n is equal to 2. This abelian surface corresponds to this lattice lambda. It's kind of complicated. I don't tell you exactly how I got it. It's rather delicate because you want to satisfy the condition star. And what is the unitary endomorphism? It will be this element 1 plus t plus divided by 1 minus t plus. Notice that t plus is a purely imaginary. It's the square root of minus b plus or minus delta. This is a negative number, so it's purely imaginary. So nu is a unitary endomorphism of C2. In fact, it acts on C2 it acts on C2 by 1 plus t plus over 1 minus t plus on one side and 1 plus t minus over 1 minus t minus on the other side. Okay, so let me now give you a very short proof of how you compute lambda. So you compute, I mean, I'm going too quickly that you fully understand, but let me write it. You know that you apply this formula. So this formula tells you that the critical value will be a square root of something. You will have as absolute value, you will have D, and then you will have a determinant. But the determinant of nu will be the product of two things. 1 plus t plus over 1 minus t plus and 1 plus t minus over 1 minus t minus. And then you develop this, and what you find is you find square root of A, and then you get 1 plus t plus to the square, and then you get, but there is a square root, so it disappears, and then you get 1 minus t minus. And this is the formula you get when you compute this determinant. And so you get a product, which is exactly the product I gave to you for the special case A equal to 1, C equal to 5, B equal to 5. And so this is equal to a square root of A plus a square root of C plus I square root of B minus 2 square root of AC. Okay, so this is why theorem implies my proposition 2 and 3. Okay, let me go on. And before giving the proof of theorem, I want to give a special corollary of theorem, which is even simpler than the theorem. And it's in the special case where the abelian variety has complex multiplication. So this means that it is constructed in the following way. You start with a number field with complex multiplication, which means that you are dealing with a totally imaginary quadratic extension of a totally real number field. So this field has degree 2n over the rational, and you choose a CM type of this field. What does this mean, a CM type? It's just, you know that there are 2n embeddings of K inside C, but you just take half of them. So just one for two complex conjugate. So you call them rho 1 up to rho n. So that all the embeddings of your number field in C are either the rho j or the complex conjugate of the rho j. Then you can introduce the so-called reflex norm of an element in K. What is the reflex norm? So it's a classical definition for people dealing with a CM number field. It's just the product of those conjugate of mu which correspond to the embedding in the CM type. If you want to compute the full norm of mu, the norm, it's the product of all conjugate of mu. So you do the product of the rho j and the complex conjugate of the rho j. So you get the absolute value of the reflex norm to the square. So the reflex norm is kind of a square root, a nice square root of the norm. Like I had this nice square root of the determinant in my theorem. So now what is the corollary? The corollary is really nicer than the theorem in the sense that what you get is a very simple formula for the critical value as an output. You get that the reflex norm is a critical value. The formula, in fact, it's up to sign. I don't know up to sign. So it's plus or minus lambda. Lambda equal plus or minus, sorry. Lambda equal plus or minus the reflex norm. One of them is critical on which group. So what is the data? So I explained to you the conclusion. The conclusion is very simple, and the data is not so complicated. You start with a CM field. So in this corollary, also what is nice is that there is no abelian variety. There is just a CM field. And you assume that it's ramified over its maximal totally real subfield, or maybe an easier condition to understand is that it is just a cyclotomic field. So start with a cyclotomic field, take an integral element inside this field, compute 1 plus S minus S bar, and with a very small assumption that the norm of this element is an odd integer, 10, you will get that this lambda is critical on the group. The group is just the quotient of the integer by the ideal generated by mu. Mu is an integer. And so this group is very nice. It's very easy to see when it is cyclic. So in particular, if you take the following example, there is this nice example where you take for S just the Lth root of unity with L a prime number, at least 5. And then this reflex norm is just this product. The product, very nice product, 1 plus 2i sine k pi over L. And the result is that up to sign, there is a plus or minus. I guess it is plus, but what I have proven is either plus or minus. This quantity is D critical for D is equal to the square of the absolute value of lambda. And in this example, you can compute this number. It's a very nice number. It's a Lucas number. And that you can obtain as this sum of two Fibonacci numbers. So what I am telling you is that here we have a D-critical value, a very nice D-critical value. And I can understand that this critical value is critical only by using abelian varieties of higher dimension, because I have to use the following abelian varieties. A is a Cn over phi of m, where n is the degree of this n is half the degree of this number phi. And what I want to stress is that this double star condition, how it is used to be sure that when you consider the abelian variety, which is the quotient of Cn by the some ideal of OK, what you get, what is very well known is that what you get is a polarized abelian variety. But what is not so easy to get is to get a principally polarized, this condition determinant one. And so there is this remark that under this condition 2 star, you get a principally polarized. And this is a remark which is an old remark due to Shimura and Taniyama. Okay. And the proof that the theorem implies the corollary is as before. I mean, you choose this abelian variety. This means you choose lambda as a lattice, and your unitary Q endomorphism is just mu over mu bar, seen as element of K, and the element of K acts on A. I mean, virtually act on A. And so if you choose this one, you get that the group is OK over mu OK. I leave the computation. And then you can compute lambda as before, as the square root of d nu, the determinant of nu. This cardinality of g nu is just the usual norm. And this determinant is the usual norm of mu. And this determinant is the reflex norm of nu. But the reflex norm of nu is the ratio of two reflex norms, the reflex norm of mu and the reflex norm of mu bar, while the usual norm is the product. So you have simplification, and you get the reflex norm to the square, but you take the square root. And this is why you prove that the reflex norm of mu is critical value. Okay. Now I have 5 minutes left. I want to explain the proof of the theorem in the 5 remaining minutes, how the strategy, what we do. So let me show you this proof. So I have written again here the theorem in blue. So we have already seen it. And what I emphasize in this slide is not only what is the critical value, but what is the associated critical function. It will be a theta function. So your abelian variety is a quotient of Cn by some lattice. So you can write the lattice as Zn plus the image of Cn by some matrix. But since we are dealing with abelian variety, tau is not any matrix. It is a Riemann matrix. And this means that it is a symmetric matrix whose imaginary part is positive definite. And the space of those matrices is called the Siegel upper half space. The symplectic group, the real symplectic group, act on it by the very classical formula, which is here. Alpha tau plus beta over gamma tau plus delta. Everybody knows this kind of formula. And when you give yourself a Riemann matrix tau, you can construct this theta function, which is a Zn periodic function on Cn, whose Fourier coefficient, here are the Fourier coefficient, Cm of theta tau, those are Gaussian function. And those are the theta function. And the theta function will be the critical function. And but to express precisely the key lemma, I need to introduce. I need some condition on the Riemann matrix, and to give you this condition, I need to introduce two arithmetic subgroups. One arithmetic subgroup is just the element of SP and Z, which are equal to 1 mod 2. And the other one is a subgroup of it, for which I impose that the diagonal matrix, if I write sigma as alpha, beta, gamma, delta, they have a diagonal equal to 0 mod 4. So this group is often called the theta subgroup. Of level 2. It is also called, because it has been introduced and studied a lot by Iguza, it is also called the Iguza subgroup. Okay, and so what is the key lemma? Is that if you start with any Riemann matrix tau, and if it satisfies that, assume you have an integral matrix D, and if you compute transpose D tau D, it is equivalent to tau with respect to the action of this Iguza subgroup. Then on the group G, which is a torsion subgroup, D minus 1 Zn over Zn, a torsion subgroup whose order is a determinant of D. And then on this torsion subgroup, if you look at the restriction of any translate of the theta function, then you get a lambda critical function for this critical value, which is a determinant. So you have a precise formula for this determinant. It's the square root of a determinant. Okay, so this is a key lemma, and this condition on the tau, you get it from the existence of the unitary endomorphism, Q endomorphism in the theorem. So it's very easy to see that key lemma implies the theorem. And to finish, in the last 2 minutes, let me give you the proof of the key lemma. So a 1-minute proof. And let me sum up the key lemma for you. So the key lemma is just a formula. It is this formula. Under some condition of tau, the restriction of a translate of the theta function to the torsion point has a self-convolution proportional to its square. So this is this equality. The sum for W in G of theta tau of Z plus W, theta tau of Z minus W is proportional to theta tau of Z square. So how do you prove such equation? So you need 3 tools. The first tool is Riemann addition formula, which tells you that before adding, you can write this product as a finite sum over 2 to the n term of functions of W times the function of Z. And this function is just a variation on the theta function that you add only on, not on the whole Z to the n, but only on the translate of 2 times Z to the n. So it's a subset. You are just summing on a subset. Okay, so if you want to prove this formula, you have to add the theta xi of W tau. This is a also well-known isogeny formula, which tells you that when you do this average, you get this theta xi function, but computed in 0 and not for tau, for transpose D tau D. Okay, So, but I have my assumption that this is sigma applied to tau for some sigma in the Igusa subgroup. So what I want to know is why this ratio, theta xi of 0 sigma tau over theta xi of 0 tau, in fact, do not depend on xi, because it will exactly give you that my two functions are proportional with a factor lambda given by this J multiplier. And why is this transformation formula correct? It's a well-known formula, in fact, which is due to, it's an output of Siegel formula, and it is due to, in this form, to Igusa. And and it just tells you that this function theta xi of 0 tau are modular functions with same multipliers on the arithmetic quotient of the Siegel upper half space by the Igusa subgroup. And I am done. I have just two questions. My last slide was about two open questions, but maybe I just stop here to be on time.
Thanks a lot for your beautiful talk.